Hi, my name is Chris Schwarz. I'm an engineer, and I work at the National Advanced Driving Simulator here at the University of Iowa. You can see it pictured right behind me. I'm going to share a little bit with you today about my own STEM journey, how I got into engineering and got this job, and the kinds of things I work on. And maybe you'll pick up a few hints and tips from hearing my journey, but everyone's journey is going to be different. So let me share my screen and take you through a few things. So that my title is Director of Modeling and Engineering Research at the National Advanced Driving Simulator. And that means I'm an engineer who focuses on research and development. We don't make new products that we sell. And there's a lot of things that other engineers do that I don't do. But I do work on research and new technologies. I was born in Moline, Illinois, which is in the Quad Cities, right on the Mississippi. And I got my bachelor's from the University of Illinois in electrical and computer engineering. And then I got my PhD also in ECE from the University of Iowa. When I was a kid, I was very interested in computers. And that was early days for computers. There weren't many of them around. But fortunately, my parents were able to buy me my first couple of computers at home. The first one was the Commodore VIC-20. It had a whole 5 kilobytes of RAM, and that's almost nothing compared to the typical 8 gigabytes or maybe 16 gigabytes that you might have today. In fact, I worked on programming my first game and I ran out of memory. I had to stop because I didn't know how to make it small enough. The first storage media I had for that computer was not a hard drive, was not a thumb drive, wasn't even a CD or a floppy disk. It was a cassette tape in a cassette tape player. And it took forever to load or save a program, and it didn't always work right. Well, my second computer was a big upgrade. It was the Commodore 64. And that computer had a lot of neat features, more memory too. I used to buy computer magazines that had programs printed right there on the page, and I could type them in. The only problem was that they were in machine language. So if it was binary, I would be typing in zeros and ones, a page full of them. Or if it was in hexadecimal, I would be typing in letters and numbers, a whole page full of them. And I wouldn't really know what the program did until I had it all typed in. But that was a lot of fun in those days. I went to school in a small school in a rural town, population maybe 1,800. We didn't have things like AP courses or robotics clubs. We just had a few Apple II computers that we could use. And importantly, I had a teacher who encouraged me to pursue my interests and gave me a few pointers. So that was so important for me, and it was enough. So my plan was that I would major in computer science in college, but my dad talked me into electrical engineering instead. See, this was 1986, and he wasn't sure what kind of future these computer things really had back then. It's kind of funny. I wasn't sure if engineering was for me. After all, I wasn't really the kind of kid who took apart my mom's appliances to figure out how they worked. So I didn't know really if engineering would be for me. But I went to my state school, University of Illinois, majored in electrical engineering, and as luck would have it, it was a very, very good place to go. It was very highly ranked nationally, great program. Well, when I got there, it was a real journey of self-discovery and exploration. And a lot of that is just a fancy way of saying I had no idea what I was doing. And I had no idea what I wanted to do. I was just adrift. I was a number at that large school. But I did make friends, spent a lot of late nights, ate a lot of great pizza, some not so great pizza. And somehow along the way, I kind of figured out some things about the large and varied world of electrical and computer engineering. There's a lot to it. So people think that choosing an engineering major is something like just choosing a field, electrical, mechanical, biomedical, aeronautical, chemical, or some other flavor. And that's part of it, I guess, but there's so much more to it. Just for instance, all the topics within electrical and computer engineering kind of boggle your mind. Let me just tell you about some of them. So you might expect that if you go into electrical engineering, you're going to be doing electronics, right? Circuits, semiconductors, making gadgets, devices. And of course, this is a huge, enormous industry. And it's something that you can do, but there's so many more choices than just this. You could get into electromagnetics, radiation, all the many different ways to use the different frequencies on the spectrum, from gamma rays to X-rays, through the visible spectrum to microwaves and radio waves. You'd learn about famous Maxwell equations, and you might work on sensors that, like radar and LiDAR, that they use on automated vehicle technology. Or you might get into antenna design or work on remote sensing, something that you could use to, for instance, map the surface of the moon or the surface of Mars. So there's so many things to do with just electromagnetics. Or you might get interested in communication theory and information theory. It would teach you how to compose a message and send it across some channel to a receiver. And that channel could be anything. It could be the telephone, your smartphone, could be the radio, could be Netflix, it could be Zoom. This area would also teach you how to compress the signal, how to encode it, decode it, encrypt it so that it is secret, decrypt it. There's a lot to this, and my engineering hero, Claude Shannon, was a real pioneer in this area. Control theory is another big part of electrical engineering, although it's also part of mechanical engineering, and it's used in many different fields, but often the courses that you'll take are in the electrical engineering department. I was interested in this area. It's so important in anything that requires controlling a process so that it's stable and it doesn't blow up on you. This could be anything from the thermostat in your house, controlling the temperature of your home, to your car's cruise control, maintaining its speed, to a self-driving car, keeping its lane and navigating through the city, to landing a rover on the surface of Mars. All requires control theory. And you can see all the different areas in this diagram. And one of them is modeling and simulation, another area that's near and dear to my heart. Image processing is another important area of electrical engineering that you might get interested in. And without image processing, we wouldn't be able to recognize faces for security systems. We wouldn't be able to recognize cars and people and traffic lights and bicycles. Technology that's used in automated vehicles. For instance, Tesla Autopilot wouldn't be able to work without intense and sophisticated image processing. So this is a very important area. Closely related to image processing is signal processing. With it, you might study physiological signals like a heart rate. You might get into reproducing speech and music, very high fidelity, all kinds of interesting applications to digital signal processing. Or you might have in mind what my dad did for electrical engineering, which was drawing and designing electrical systems for homes and businesses. Maybe not the most glamorous part of electrical engineering, but incredibly important. Well, I was interested in all kinds of things, maybe everything, but as a result, I never really focused on anything. In fact, during my job fair senior year, I applied for a lot of jobs, and I got to apply for my dream job with NASA. I thought, wouldn't it be cool to work on a Mars rover or the International Space Station? Maybe even get to go there myself. But when the interviewer asked me, what do you want to work on? My mind just went completely blank. And I said something dumb like, um, maybe it would help me if you explained what you work on. He just kind of looked at me funny, and I didn't get that job. In fact, I didn't get any of the jobs I applied for that year. The job market was bad, it was true. But really more important than that, I still didn't know what I wanted to work on, who I wanted to be, what kind of engineer I wanted to be. So I decided after that um, I found a job, and my dad kind of saved me there. He found me my first job in electrical engineering, and it was working for a consulting firm doing electrical design up by Chicago. And I did that for a couple of years and got great experience, but it became clear after that time that this wasn't going to hold my interest long term. So that's when I decided to do what a lot of people do, and that's go back to graduate school, which is really another way of postponing a decision about what to do in some cases. For me, it was. But that's when I got to Iowa City in 1993 after a summer of intense flooding, and I decided that I wanted to work in control theory. I picked an advisor, started taking classes, still not really knowing what I was doing, but I knew I had made the right decision because I was having a great time learning again. Um, and I was where I needed to be, even if I didn't know what it was leading to. But during my studies, somebody contacted my advisor looking for a graduate student to work on vehicle modeling and simulation project. And that's how it was that I came to work for the NADS, the National Advanced Driving Simulator. That was 1996, and that's a whole 4 years before the simulator was even built. We were working on this software. And when I graduated in 1998, I applied for a full-time position and got it. And the rest, as they say, is kind of history. Almost everything that we do with the simulator involves some kind of modeling and simulation, which, if you remember, was a subset of control theory that I was studying. But what is modeling and what is simulation? Well, in our case, for the simulator, we often are modeling a car or a truck of some kind, but a model could be something super simple, like collecting a series of balls of different sizes and using it to model the solar system. That's a model. But a feature of models is that none of them are 100% accurate. They're all wrong in some way. But we make them anyway because models are useful in some way. And then there's simulation. A simulation is just a model in motion, a model that evolves over time. In our case, we hook up some inputs to that model that come from a real person pushing a pedal or shifting a gear. We let that model change and accelerate and move through the world, and it creates signals of velocity, position, of acceleration. And then we connect those outputs to a graphics system and a very large motion base, and we have a driving simulator. I'm going to play a short video for you that talks more about the simulator and what we use it for, and some of the technology that goes into it.
Automobile safety has come a long way in 100 years, from seatbelts to airbags to collision warning systems. But along with these improvements have come higher speeds and more traffic. Given how dangerous driving can be, how do we design safer cars, informed by the way people actually drive? How can we achieve realism without the actual risk? The National Advanced Driving Simulator at the University of Iowa addresses this with a high-precision tool that recreates the experience of driving, the NADS-1 simulator. This high-fidelity ground vehicle simulator was the first of its kind in the world and provides the most realistic virtual driving experience available.
Our mission is to help save lives. We believe that by having a tool that allows us to put human beings in a very safe and controlled environment, but yet allows them to drive like they would in the real world, a tool like that is invaluable in trying to figure out how we can lower the loss of life.
The NADS-1 consists of an entire vehicle inside a 24-foot dome with a wraparound 360-degree visual display system. A motion base with 13 degrees of freedom accurately reproduces the sensations of accelerating, braking, maneuvering, and interaction with the road surface. These features combine to give the NADS-1 an unparalleled level of realism.
Most people, they have a pretty good sense for what driving feels like. So we have to have a tool that replicates that driving experience really well, because the whole premise of the research that's being done on the tool is that when people get in and they drive the NADS-1 simulator, that they truly believe that they're driving a car.
A major study at NADS evaluated electronic stability control, an active safety system designed to help drivers maintain control of their vehicles in adverse conditions. Because research was able to show that the system was effective, the National Highway and Traffic Safety Administration made ESC a standard feature in light vehicles, estimating the system will save thousands of lives annually. Research in NADS isn't limited to study.
We also, these days, have a small fleet of on-road vehicles that we use for research. We have a Tesla Model S with autopilot, and this one pictured is a Lincoln MKZ, also with features of self-driving. And we use these cars to study how people interact with the technology on real roads and real traffic. Because sometimes being on the road and in reality is just a slightly different experience than using the simulator. And so we're getting into, so we do a lot of research in that area right now too. Well, I've been able to work on so many different interesting topics here in my time at the simulator. Really advanced technology like adaptive cruise control, autonomous emergency braking systems, and self-driving cars. It's been really interesting, and it's a multidisciplinary experience, meaning that the center needs a lot of different types of backgrounds and educations in order for everything to work right. So we have engineers like myself, we have computer scientists and programmers, we have psychologists and human factors experts, we have hardware engineers, and we even have graphic artists who come to make the environments. And we also routinely employ students to help us run studies and just get the job done. So in my time at the simulator, I've learned a lot. It's true, I have used my education in a lot of different ways, but I've had to learn new skills and new things over the years. While I took control theory in school, it was a completely different story to try to apply it to this $80 million simulator. And while I took signal processing in school, that didn't really help me to um, use the signals that were coming out of the simulator, reduce them, analyze them, and make interesting and useful conclusions from our studies. I had to learn how to do all that using the things I learned in my classes. Since I've graduated, I've learned about machine learning, applied it to human behavior models. Really, today my skill set is in some ways more like a data scientist. And if data science is something that you're interested in, it's a very hot topic today. There are a lot of jobs on data science. But interestingly, a project I'm working on right now has really taken me back to my ECE roots in a way that no other project really has for years. I'm putting a radar inside a vehicle, and the purpose of the radar is not to look at other vehicles, is to look at the driver and the motion of their chest. And from the motion of their chest, measure respiration, their breathing rate, and their heart rate even. And you can imagine by being able to monitor the driver's vital signs in this way, we can say something about their state, whether they're healthy, whether they're impaired, whether they may be having a cardiac event, perhaps whether they're drowsy or intoxicated. So this type of in-cabin monitoring is really promising and is an active topic of research for a lot of labs around the world. And if I didn't have my background in electrical and computer engineering specifically, I would never be able to work on this project that came my way. So did I have any idea where I was going to end up back when I was playing with that VIC-20 and the Commodore 64 in my basement? No, I had no idea. And to be honest, I still had no idea when I was at University of Illinois. And I still had no idea when I was at University of Iowa. But I did do some things right. I said yes a lot. I was open to new opportunities and I didn't turn things down, even if I didn't know where they were going to lead. I stepped out of my comfort zone a lot and tried new things and talked to new people, which was not always easy for an introvert like myself. I was persistent. I didn't give up. I just kept on going and followed my interests. I was curious. I learned new things. I always tried to improve myself. Another example, there was a time when Stanford was offering an online class in artificial intelligence, and more than 100,000 people signed up for it, and I was one of those people. As these things go, you may not be surprised that all 100,000 of the people did not finish the class. Probably less than 1,000 did, but I was one of those people who finished and got a good grade in the course because I was interested in it. And in fact, I learned through that course a lot of the technology that goes into self-driving cars, automated vehicles, and it set me up in many ways to work in that field several years later. So it was another example of following my interests and being open to doing something new helped me out later on down the line. So my STEM journey has been a great adventure. I really enjoyed it, and I encourage you to start your own journey and follow it wherever it takes you. Good luck. Thank you.